Good. So as you'll recall, we're taking kind of a leisurely stroll through chapter 4 because I set aside 3 class days and really 2 was probably enough. But if we still have extra time at the end of Friday's class, I can always just start in on chapter 5 because there are some fairly complicated ideas in chapter 5. So nothing wrong, especially after an exam day, with having a somewhat more relaxed class, the way I figured. I want to cover 3 main topics today. There's one more issue about the structure of benzene that I want to cover that's a little bit subtle. And I do have to say, your book, the way your book covers it is well above average compared to the textbooks that I have been looking at for 20 years, which may be of small comfort to you, but I especially liked the way they explained it. And in fact, when I looked at how I usually explain the topic and compared some time ago to what your book has, I'm basically gonna take it straight from your book because I like how they did it better than the way I usually explain it. So there's that. Then we're gonna spend some time on nomenclature of aromatic compounds. And then if there's time left over, I actually want to pick one topic from what would have been Friday's class. That way we don't need to rush through all the reactions and we can just do one topic on Friday. And that has to do with polycyclic aromatic hydrocarbons. I won't have a lot to say about it, but I think it's an important topic if for no other reason than as kind of public service, because polycyclic aromatic hydrocarbons, or PAHs as they're known, are kind of dangerous for reasons that we'll get to when we actually talk about that. There is something that you want to avoid if at all possible. Good. So we've already discussed how benzene is what we call an aromatic compound. The term aromatic or aromaticity, these are not uniquely defined concepts. And another somewhat subtle point that I feel nevertheless ought to be brought up. What I mean by a uniquely defined concept is that aromaticity isn't something you can stick a probe in and measure and get a number out. It's not like that. You can't say the aromaticity of a compound is 11. An example of something that is a uniquely defined concept is pH. Right? If you have a solution, you stick a probe in and you can say the pH is 8.3 or 2.8 or whatever the heck it might be. Aromaticity doesn't work like that. Rather, aromaticity is kind of this loosely defined conglomeration of properties that benzene and compounds that are like unto benzene all have, a certain set of reactivities. And so that's what we're studying in this chapter. So basically, aromatic compounds are those that behave like benzene. And there are some, including the polycyclic aromatic hydrocarbons. There are a few others that I don't think we're going to run into too many of. Like I said, we might meet some in the heterocycles chapter. In fact, I'm fairly positive we will. We can worry about that at such time. I don't think I really need to spend a huge amount of time on those. But certainly the star of the show in terms of aromatic compounds for us is going to be benzene and derivatives of benzene. And benzene has another property that is called its resonance energy, which is, again, there are those who would say it's kind of bogus, but I think it's a reasonable point to bring up. And your book talks about it, and it needs a little bit of explanation. So that's why I'm going to spend a little bit of time on it. I just want to make sure that when you read what the book says, it makes sense to you. So that's why I'm talking about this. Just a word of warning, this does involve numbers and math to a small extent. Of course, these numbers, I don't care if you memorize them. That's never our point. I'm not into you guys just memorizing numbers. I don't think it's a good use of your time. I know I say that a lot, but I really don't. So the idea is this. We already know that you can take an alkene such as cyclohexene, you can treat it with hydrogen gas and palladium or platinum or nickel catalyst, and you will get cyclohexane. One could imagine doing the very same thing to 1,3-cyclohexadiene, which is a compound that exists, and you absolutely can do the same thing. You can treat that with hydrogen. You will need at least 2 mole equivalents, of course, since there's 2 alkene double bonds. And again, palladium or platinum or nickel, your choice, any of those three coinage metals that are right in the same column of the periodic table, same thing, you will get cyclohexane. What about benzene? Can benzene be hydrogenated? Answer is yes. You, of course, need 3 equivalents of hydrogen, but it's a good deal more difficult to hydrogenate it. You need to use rhodium metal, which, let me look on my handy dandy periodic table. Rhodium is element number 45, in case you're curious. It's right under cobalt on the periodic table. And it's a significantly more reactive metal than nickel or palladium or platinum. And you would, of course, also get cyclohexane. So you can do that. It's just a good deal harder. And I think you can see we've got kind of a series here. We've got first 1 double bond, then 2 conjugated double bonds, meaning they alternate, but double, single, double, and then 3 conjugated double bonds. And it looks like we have a reasonable series here. And we could learn something about the data on this reaction. The heats of reaction are known for all of these, and you would think we would get like a series of numbers that make sense to compare, because we're very much comparing apples to apples. And so the book gives these numbers. The heat of hydrogenation, or the heat of the enthalpy of this reaction is, and as you see, I'm looking it up, I don't have it memorized, minus 28.6 kilocalories per mole. And we're just giving the numbers again so we can compare them. The enthalpy of this reaction, that heat of hydrogenation, is minus 55.4 kilocalories per mole. So these are exothermic processes. It does actually release energy to hydrogenate double bonds. And if you work it out, you can see that just as we would have expected, this figure of minus 55.4 kilocalories per mole is roughly twice the other one, minus 28.6. Not exactly, but I think you'll agree it's pretty darn close. As you would expect, we're going from 1 double bond to 2 double bonds. So that very much makes sense. What about benzene? Well, at first glance, you might think that benzene would then be about 3 times this figure, and it's not. It's minus 49.8 kilocalories per mole. And of course, as I said, I don't expect you to memorize any of these numbers. That's not the point here. But we can draw some conclusions based on this. We would have expected to get, oh, I don't know, maybe minus 80 kilojoules per mole, something like that, somewhere in that range. And we're getting significantly less than that. We're off by about 34 kilocalories. Did I say kilojoules? Kilocalories per mole. I'm used to using joules. I do research with Dr. Singleton and his research group over the summer, and they always make fun of me for wanting to use kilojoules. So I get, it's kind of a long time private joke with them. They, that I'm a joules man instead of a calories man. But you can use whichever. You would find the same thing, by the way. To get it into joules, you just multiply all those numbers by 4.184, and you get the same data in joules. Either way, you'll find that we're off by a good amount on benzene. We would have expected a figure closer to minus 80. Instead, it's more like minus 50. And so that difference of 30 kilojoules per mole is because benzene is so much more stable, so much lower in energy than we would have predicted if benzene were just a cyclic triene. So what this shows us simply is benzene is not just a cyclic triene. Something special is going on with benzene, which we've already talked about. And all these numbers and all this data is meant to show us is just proof that benzene is significantly more stable than we would otherwise have expected. That difference of 30 kilocalories per mole or so shows us how much more stable benzene is than a would-be cyclic triene. So we already knew that benzene was not an alkene. Hopefully you've got that down based on the couple of classes where we've been talking about benzene and benzene derivatives. And honestly, that's one of the main points of this chapter. Benzene is not an alkene. I would say if you've got that much so far, you're doing pretty well. You're tracking okay. That's one of the main points. And all this data is meant to do is to show that numerically, that benzene is not an alkene. And that's what these numbers are showing. They're showing us that we would have expected a very different heat of hydrogenation if benzene were a thing fundamentally like cyclohexene or cyclohexadiene. So benzene is not just a fictitious cyclohexatriene, it's something else. And that's really all this is trying to show. And I just wanted to spend a little bit of time on that because it's not the most, let's say, approachable material you'll find in your textbook. And sometimes, for very understandable reasons, people see all these numbers and they freak out, which I get that. I mean, if I just see a bunch of numbers for no apparent reason, you know, I start to wonder what's going on myself. So that's why I wanted to spend a little bit of class time explaining this, so that you understand it when you read what the book says. But that's really the only point here. You certainly don't have to memorize all those numbers. I would never do that to you guys. Good, so that's pretty much the first point. I also want to talk a little bit about nomenclature. And of course, nomenclature is always, or naming is always a relevant topic when you're talking about any new functional group. And you'll start to notice that, I think. We'll start getting into individual functional groups. We'll talk about alcohols and how they behave. We'll talk about ketones and aldehydes. They kind of belong together since they behave very similarly, and how they behave. And we'll discuss esters, let's say, or carboxylic acids and how they behave. And each time nomenclature kind of comes up. And again, the great thing is, once you know something about naming alkanes, you know the vast majority of what you need to know to name anything else. And I would say most of that remaining 20% is going to come in aromatic compounds. But there's still going to be some ideas and rules in common with naming anything. So since there are some extra terms to present, and some particular aromatic compounds that are important to know, I think it's worthwhile spending some time on that. And so if I even take until 2:30 on nomenclature of aromatic compounds, I think that will be fine. Even 2:35 won't be the end of the world, because I think we can handle polycyclic aromatic hydrocarbons in just a few minutes. Good. So first of all, when you look at the material on nomenclature of aromatic compounds, you'll find that there's about 10 important particular aromatic compounds to know their names. And by the way, one of those 10 is benzene. So we already know that one. And the reason is those other 9 compounds were named so long ago, maybe 150 or more years ago, that they just have very, very old names that have stuck. And so those are still used to this day. And you already know where I stand on just memorizing reams of data. I'm not a huge fan of it. I don't love making my students do that. But, and there's, by the way, there's a lot more than those other 9 plus benzene. There's, you know, dozens or hundreds of other, certainly dozens of other aromatic compounds that have very, very old common names that are still used today. But these other 9 besides benzene are so common that I think it's going to be a stumbling block if you don't learn them. And so since we have the time, I might as well introduce them to you. Of course, you know benzene. We've had that one already. And I'm using the circle here because I like to do so. If you'd rather draw out the double bonds, go ahead. Again, as long as you're aware that benzene doesn't really have double bonds. Methylbenzene is called toluene. Isopropyl benzene is another real common one. It's used industrially a lot. There's lots of polymers that are used making cumene. And so isopropyl benzene is called cumene. Isopropyl benzene is not wrong, but I want you to know these so that if cumene or toluene get mentioned, you understand what they're talking about. And like I said, I realize at this point I'm basically copying out of your book, but we have the time today, so I might as well use it. Styrene. Styrene is vinyl benzene. These are also listed in your book, by the way. Styrene is vinyl benzene. Phenol is hydroxybenzene. And by the way, not to add an 11th, but remember, benzyl alcohol is a different critter. Benzyl alcohol is CH2OH, not just OH. Benzyl alcohol. Very common mistake, mixing up phenyl and benzyl. And it's very unfortunate, but we're stuck with it. So please be sure to tell the difference between phenol and benzyl alcohol. They are very, very different critters. Phenol actually has some importance in its own right. Phenol was used as an antiseptic already 100 years ago or more in hospitals, and it's still used as an antiseptic to some degree today. You'll find a little bit of phenol in like Listerine mouthwash. And if you get that old school Listerine that's kind of a yellowish brown color that's sort of unflavored, that kind of unpleasant taste is due to phenol. It's got a few percent of phenol. It's kind of toxic, but so don't go drinking the whole bottle, which I don't think you're going to do anyway. But in small amounts like that, it's not a concern. But of course, in the Listerine that has nice colors, they also add nice flavors to some degree cover up the phenol flavor. Good. So let's see, what else? Anisole. Anisole is methoxybenzene, so ANISOLE, anisole. After that, benzaldehyde. Benzaldehyde is benzene with an aldehyde functional group on it. While we're going over these, benzaldehyde's a funny one. I probably mentioned when we covered the aldehyde functional group that most aldehydes smell really disagreeable. You've probably smelled formaldehyde if you did like dissections in biology class in high school. You're familiar with what formaldehyde smells like. Pure formaldehyde is actually a gas. And so the liquid that they use to, preserve specimens is an aqueous solution of formaldehyde. And most aldehydes smell something like that, really unpleasant. Benzaldehyde, for some reason, is an exception to that. I can't tell you why, but benzaldehyde smells extremely pleasant. People do disagree a little bit. Some people say it smells like maraschino cherries. Some people say it smells like almonds, but pretty much everyone agrees it smells very nice. No idea why. It's just the way the smell receptors in your nose work. Good, so that's benzaldehyde. I think next I'd like to do, I'm going a little out of order from your book, but that's okay. Benzoic acid is benzene with a carboxylic acid functional group on it. So benzoic acid. And so esters of benzoic acid are called benzoate esters. You could have ethyl benzoate or methyl benzoate. But benzoic acid is that one. Acetophenone, I'm going to move it over here just because it's a little easier. Acetophenone, ACETOPHENONE. Acetophenone is basically methylphenyl ketone. And then one last one, aniline. Aniline is aminobenzene. ANILINE, aniline. And so these are the ones you'll find in your book also. They're already in your book in kind of a list. And it's like I said, I am not a huge fan of just cramming a bunch of names down your throat, but these compounds show up so often that I really think you're gonna have trouble if you don't know these names. And we could go on. I could probably come up with 10 more, but these are the most common ones, the ones that I think are worth learning. And as I said, one of them is benzene itself, which you already know. So that's the only reason. I am not into saying memorize these 10 compounds because memorize these 10 compounds because I said so. I think there's good reason to learn these because we're going to be using them. And I think that's really all I need to say about that. Good. Oh, yes, I'm sorry. Well, only because it's separate from those 10. See, because, or it's also not one that's in your book. But the other reason I'm putting it here is because if you just, I don't mean you personally, but if you just hear the term benzyl alcohol, you might be tempted to think of this, but that's not benzyl alcohol, it's phenol. benzyl alcohol looks like this. It's that word benzyl. It's very unfortunate, but we're stuck with it. We just came up with it years ago, so 150 years ago. So I would say the reason I put it in parentheses, really the whole thing's in parentheses, is because it's not in that table in your book. But I'm just mentioning it for comparison purposes. Yes. That's an aldehyde functional group, C double bond O OH. Oh, sorry, C double bond O H. I could have done the double bond a little better. Let's see. Yeah, C double bond O, then H. It's an aldehyde functional group. Good. Other questions then? Incidentally, I didn't really do this consciously, but you'll notice I've already stopped putting lone pairs in the oxygen. You may do the same. I like holding to that and being kind of picky about that, at least through the first exam, or at least round and about there. But of course, all of these lone pairs are still there, right? So you can add them. You can add them if you like. It's never wrong. But basically, often those lone pairs are left out. If you're just drawing a structure, unless you're trying to make a point, perfectly okay with oxygens, nitrogens, things like that. The only time we really are careful to put in, actually, it seems to be reacting to the screen. I didn't think it would do that. The only time we're really particularly careful to put in lone pairs is especially when we're dealing with atoms that have a non-zero formal charge. So if you're looking at a carbanion or something like that, then we really need those lone pairs. Good. So let me see. Couple other ideas on nomenclature. Let's talk about disubstituted benzenes. I think you'll agree, and I'm just putting like black dots here. These two groups can be anything. But I think if you put two groups on a benzene ring, you'll agree there's three possibilities, and they're different from one another. One is to have the two groups right next to each other. Another is to have them in kind of a 1-3 relationship. And the last one is to have them directly opposite from one another. And again, those big black dots can be anything. Yes? Oh, disubstituted, two things attached. And what we're saying is there's three different ways you can attach two things to a benzene ring. So disubstituted benzenes. They're all different, those three. And so they're going to need different names. And it doesn't matter if the two groups are the same or different ones. There's still three different ways to put them on, and those are they. And they have different names. You can call this one 1,2 disubstituted, or you can also call it ortho. And the abbreviation for ortho is just lowercase o. This is 1,3 disubstitution. Again, I think for pretty obvious reasons. It's also called a meta disubstitution, and you can use a lowercase m for that one. And then last but not least, we've got our 1,4 disubstitution. That's also called a para substitution, or lowercase p. And those two possibilities in each case are equally fine. And I just wanted to put that out there. We'll do a bunch of examples now, but I just wanted to show you some cases of where these things are used. Let me actually see if I can move that up a little. Whoops, I didn't really mean to do that. There, that's fine. Just wanted to make sure everyone can see. Good. So just some examples of how these things are used. If we had this compound over here, and again, same thing. You can put the 3 lone pairs on each bromine if you want to, but it's understood perfectly fine without it also. So either way is fine. The only time you really have to draw the lone pairs is if you're using them to make a point, or you're using them to draw a mechanism, let's say, using curved arrows, which again is something we will do a little bit in this class, but not very much. So if you're just drawing a structure, normally you don't have to draw them. You can, but it's optional. You don't really need to. Watch OWL, because you know OWL will be OWL. Usually they don't require it, but make sure you read the instructions and see if you need to put the lone pairs on. Good. So this guy could be called either 1,2-dibromobenzene, or ortho-dibromobenzene. And which of those two names is better? I would say they are equally good. They are equally correct. Either one of them can be used. They're both just fine. We'll do another one. Let's look at this guy. Here we have two ethyl groups. And of course, if you number them just like we numbered this 1, 2, you could number this 1, 2, 3, 4. Or you could go in the opposite direction, you'll get the same thing. We could call that one 1,4-diethylbenzene, or para-diethylbenzene. Either of the two is perfectly fine. I do not care which you use. They are exactly equally good. They're both correct. And I have a bunch of other examples here. So what if the two groups are different? Well, if the two groups are different, then you need to see, first of all, if one of those groups is one of these 10 over here. If one of the groups is, for instance, an isopropyl, then you'd probably name it as a cunene. If one of them is a carboxylic acid group, I would think you would name it as a benzoic acid. So I have some examples of that. Let's look at this one. We'll put an aldehyde functional group over here and a tert-butyl group over here. So we're going to name that as a benzaldehyde derivative, since one of the groups is a benzaldehyde. And since we're naming it as one of the groups, rather, is an aldehyde functional group, which we have over here on benzaldehyde. And since we know we're going to be naming it as something or other benzaldehyde, by definition or by convention, carbon number 1 is going to be the carbon that bears the aldehyde functional group. So that guy you could call either 3-tert-butyl benzaldehyde, or you could call it M-tert-butyl benzaldehyde, either way. And of course, if you use the number, you don't say 3-tert-butyl 1-benzaldehyde, because carbon 1 is understood to be the one that has the aldehyde functional group on it. But either of those names is perfectly fine. And again, if you were to try to get me to commit to which one is better, you couldn't do it. I say they are equally correct. Those two names are equally correct. I have one or two more. Maybe I'll do one up here, drawing lines everywhere. Let's put a chlorine on and a vinyl group on, as that group is called. And you can see we can find one of those vinyl groups over here. Vinyl benzene is called styrene. Vinyl is CH double bond CH2, VINYL. Vinyl group. So that's what that group is called. And so vinyl benzene is called styrene. So let's call carbon 1 the one that bears that vinyl group. Carbon 2 is the one that bears the chlorine. So we would want to call this guy either 2-chlorostyrene, or any wild guesses as to the other name? Orthochloro, or O-chlorostyrene. Yep. Either way is fine. Stipene. I don't even know what I'm doing. Or orthochlorostyrene. Either way, equally correct. What if there's more than two groups attached? Then you can't use orthometa-para if there's more than 2 groups attached. So if you had something like, oh, I don't know. Let's do 2 more like this, maybe. Sort of tired of bromines. We'll use them anyway. Who cares if I'm tired of them? Let's say you would something like this. Well, you would want to call carbon 1 the one that bears the OH group, because we're going to name this as a phenol. Phenol is hydroxybenzene. And then we got to keep going. 2, 3, 4, 5, 6. And if you numbered it counterclockwise, you'd get the same numbers. So I would call that guy 2,6-dibromo phenol. And that's the only correct name. You can't use orthometa and para because there's more than 2 groups attached. So if there's more than 2, you have no choice. Since we have time, let's do one more. Also, since I wrote it in my lecture notes. Let's see. Methyl group over here, fluorines over here, and ethyl group over there. So we know that methylbenzene is toluene. So I think it makes the most sense to name it that way. And by the way, you'll get lots of practice doing this on ALO, but I just wanted to give you some examples beforehand. So, we'll call carbon number 1, the one that bears the methyl group. Looks to me like we have fluorines on 2 and 6, and an ethyl group on carbon 4. Alphabetically, E comes before F, so ethyl comes before fluoro. So I think the best name for this is going to be all one long word. I would call this guy 4-ethyl. There's a hyphen in here. 4-ethyl 2,6-difluoro toluene. And that's about as crazy as I could come up with, unless you start putting on 5 and 6 groups. But I think that's enough to give you the idea. So again, you can only use orthometa and para with something that has exactly 2 groups attached to the benzene ring, replacing hydrogens. Any more than that, and you have to use numbers. So that's that guy. Yes, or just stretching. Oh, okay. Yeah, it's understood that carbon 1 is the one referring to toluene. So it must be the one with the methyl group. Just like over here, we don't say 3-tert-butyl-1-benzaldehyde because carbon 1 is assumed to be the one that bears the aldehyde functional group. For what, sorry? It should. I mean, and if it's one like these, I would expect it to accept either answer, unless it says something like use orthometa para or use numbers. So especially with ALO, you have to read the directions carefully. One bit of feedback I've gotten, by the way, for better or worse, is that my exams are clearer than OWL, which I forget who said it. I think it was one of the English poets. I've heard the phrase damning with faint praise, which, you know, if faint praise is all I can get, I'll take it. But yes, you do have to read OWL carefully. They usually do say what they mean, but you have to read them carefully. But yes, if they don't specifically say, I would think it would accept either. Certainly I would. Good, other questions then? All right, well, let me clear that out. That leaves us just to cover PAHs, or polycyclic aromatic hydrocarbons. And who knows, I may get us out of here 4 or 5 minutes early. I assume there will be no objections. I especially think it's fine considering we just had an exam. Good. So there are many compounds that have multiple fused aromatic rings. And I'm just going to put a couple. Oh, I'm sorry, question? Or no? Oh, you're fine. It's okay. That's okay. I'm just going to put a few here. I don't know if I really care that you memorize these ones, but they do have names, so I'll let you know what they're called. Naphthalene you might actually have heard of. And you will notice with these, I actually don't like drawing circles. I feel once you start fusing benzene rings, it gets a little unclear. I think it's much clearer when you put the bonds in. But we still have to remember these are still resonance stabilized species. They're still not localized double bonds. So these creatures are very much like benzene. They have multiple resonance structures and they have a resonance energy to them. But that one happens to be called naphthalene. And the only example I can think of with naphthalene is if you've ever smelled mothballs. The thing that you smell is naphthalene. Mothballs, I believe, contain naphthalene and benzoic acid of all things. So, but if you've ever smelled mothballs, it's naphthalene that you're smelling. Phenanthrene. These actually begin to be a little difficult in terms of where to put the bonds. But lucky for me, I did it ahead of time. That guy happens to be called phenanthrene. Again, I don't really care if you memorize these names, but they do have names. And I'll just do one more. There are dozens of these that are known. Let's see. And that guy is called pyrene, P-Y-R-E-N-E, pyrene. And we could go on. There are others besides these. They're called polycyclic aromatic hydrocarbons. And I think it's worth spending a few minutes on these guys because they're bad actors. These guys are carcinogens. Maybe naphthalene less so. Again, I wouldn't go rubbing it all over yourself. You know, it's not the nicest stuff in the world, but I would say the more benzene rings, and we went up to 4, and there's multiple different ones with 3 and 4 benzene rings, and the possibilities get more and more as you start adding more. But all of them, not a one of them is good for you. And the more benzene rings are involved in the fused polycyclic aromatic system, like I said, these are called PAHs. So if you ever see PAHs mentioned, that's what they're referring to, polycyclic aromatic hydrocarbons. And again, not a one of them is good for you. And the more benzene rings, the worse it is for you. They tend to be carcinogenic. So these are bad actors when they get into the soil, they get into the water, then it's a problem. Where do they come from? I think you will mostly find these, well, they come from you'll mostly find these from combustion processes in general. So you worry about finding these things in smokestacks, for instance. Another place that's a little more consumer-oriented where we find these things on the regular is anytime you grill well-done meat, all that black stuff will contain some of these things. So, I mean, I would say don't go eating 50 well-done hamburgers every day. I doubt you were going to do that anyway, but it's not good for you. The amount in one hamburger is pretty negligible. But you do find these as a product of combustion. So they are of some concern. I don't know if you guys may get exposed to these or have the potential to be exposed to these in any of your jobs later on. But it's one of those things that I don't mind spending a couple of minutes on. You want to watch out for these. They are definitely bad for you. And with that, I think we've done enough for today. That will allow us just to cover the aromatic reactions, electrophilic aromatic substitution on Friday. So I assume there's no objection to getting out 4 minutes early. So have a great day, and I will see you all on Friday.